All right. Okay, well, welcome everybody. I know we are literally in the middle of a take-home exam right now, so your brains might not feel like they have the most space for new stuff, but we must press on because today, which would normally be like after I force you to like sit in this room for a hot, sweaty hour and do the midterm, right? Today we are starting the second half of this course. There will be some topics kind of like, I call them the grab bag at the end of the course, which is like stuff that Casey thinks you should have in your brain so that at the end of the course, somebody's like, did you take data structures and algorithms? And you're like, yeah. But other than that little bit of grab bag of topics, pretty much from here on out, the rest of this course is going to be about this one particular idea, something called graphs. And if you were like, wow, Casey's enthusiasm for computer science is way too much, get ready, because this is my favorite part of the course. I'm obsessed with graphs and graph theory. So that's what we're going to be talking about for at least the next 3, if not 4 weeks. Before we get into that, let's talk about the thing currently at hand. So we have this simulated midterm out. Again, thank you for your patience. I just want you to know, like, we are literally inventing this as we go if I haven't mentioned it. So I know that the red edges can be a little rough. I promise that we're not trying to put any of that burden on you. So if things are confusing, please thank you for using the ed board. The TAs are keeping an eye open on that. There was a bit of confusion about whether or not the design portion was due today at noon or today at midnight. And then I figured let's err on the side of safety. So the design will be due tonight at midnight because I didn't want anyone to miss it. There will be no late assignments. Now, keep in mind, the way we're going to grade this thing is we're going to look at what you do for part 1, and then we're going to look at what you do for part 2, and it's that holistic picture. Meaning if you do something for part 1 that is a sincere effort, but is not at all correct, like you just totally misunderstand or you get it wrong, that is not a problem. You can still get absolutely full 100% on this assignment as long as your review shows us that you've learned and understood and reflected on your design. So the design will be due tonight by midnight. Then we're going to close the grade scope. We are also then going to post the staff solutions. Now, I'm calling it staff. I should really call it staff designs, not staff solutions, because hopefully you've looked at it by now. Oh my gosh, please look at it, please. I just realized. But you've probably noticed there's a lot of different ways to solve this problem. And there's a lot of different ways that are equally as optimal. It's a little bit about how you sort of interpret the problem, how you articulate the problem to us, what you want to optimize, so on and so forth. So we'll release our solutions. And then for your review, what we want you to do is look at what you wrote out, look at what we wrote out, and just sort of reflect and tell us, hey, are you sticking with your original design? Would you make any changes to your design? Was your design, optimized as appropriately? So the second portion of the midterm, the design review, will be due on Wednesday, May 4th. It's Star Wars Day. It's midnight. Yeah, okay. And keep in mind that we will be then releasing Project 3 on Wednesday. So hopefully you've had some break from your programming assignments and some break from your exercises to work on this midterm. I think those are all my official announcements. I'm going to answer some of the questions that came into the poll everywhere, but does anybody have any questions right now that they want to ask about this whole process that we're going through together? Okay. The number one question on the poll everywhere is how long should part 2 take? So if you remember exercise 3, that's exactly what you're doing for part 2. So that was us trying to give you a little bit of a heads up. So remember for exercise 3, you looked at someone's design according to a scenario and then you filled out the review. Now you're filling that review based on your own design. So it's tough for me to say how long it would necessarily take. I'm hoping that it maybe takes you an hour of thinking and writing and doing all those sorts of things, but we all sort of progress in different times, but just part 2 is literally what you did for exercise 3, just for your 2 designs. How many points can we get back from revisions? Yes, so we are not applying any points to any individual piece. The points are evaluated on the whole. So it's not that like we're going to grade the first part, take away points, and then give you back points for the revision. We're instead going to take the two pieces together and ask ourselves, does this represent somebody that fully understands how to select a good ADT, how a data structure fits into that, how to choose designs based on optimality, how to review their own designs. So, like I said, if you say, do your first design and you fully understand it and you come up with a beautiful design and then you look at the staff solutions and you're like, you know what, I like my design even better. And then we look at it and we agree. Your review could just be as simple as like, I crushed it, first version, totally nailed it. Or the opposite direction, maybe the first one, not on the mark, could be totally wrong. Your review could then be probably will have to be a lot more detailed, right, in explaining what the differences are. So I think in that particular case, that might be the big differential in time, but those two solutions would get the same grade. Cool. Hi. Hey, thanks for putting things in here. Just sending this in for credit. Muffin, what's up? I appreciate it. Okay, let's see. I'm just reading through the poll everywhere really quick. Let's see. Is it possible to get a high grade, not as optimal? Yes. Oh, can we use multiple ADTs and data structures for different functions? Yeah, you can. If you would like to do that, you can. I will tell you, you don't have to. So if right now you're like, oh, I only did one, and if I totally messed it up, you don't have to go back and like change things. But if you're like, you know what, I think this ADT data structure works better for this function, and this one works better for this one function, as long as you can communicate it to us, we will take it in. This is absolutely that situation of technically correct wins the game. So as long as your thoughts in your grade scope reflect a design that we think works, we will give you points for it. And if that means you want to use multiple structures, you're welcome to do that. When can we expect to receive the grade for the midterm? So the TAs have voted, and they want us to all just get in a room together and bang this thing out. So we're going to get in that room on Friday. We're going to see how long it takes us to grade this. Like I said, this is the first time we've ever done anything like this, and I honestly do not know how long it's going to take us to grade. So I'm hoping that we'll be able to say have your grades released back to you in, say, a week from Wednesday. That's my goal, but I will keep you posted. Cool. Just scrolling. I think that's kind of the top ones from here. Any other questions on the simulated midterm? Cool. We'll do a big round of feedback, anonymous feedback after this, and you can tell me, you'd be like, Casey, this was awful, I hate it, or Casey, here's how you fix this thing, it's close. So I would love to hear your thoughts on it after this. Okay, cool. Well, then let's take a break from thinking about the simulated midterm for the next 40 minutes or so, and talk about something new. Let's talk about this thing called graphs. So we started very first week of this class reminding ourselves about this idea of arrays. And an array is just like, that is like the foundational memory unit of the computer. All memory in the computer is technically an array. And what is an array but inherently a linear group of data that is all the same type? So it's really more of like a category. It's like a bucket that can store all of one thing, right? Typically, these are sort of like independent entries, but they all have some sort of like categorical like relationship to one another. So maybe, for example, you have an array that's all of your student numbers. Each student is kind of independent of one another, right? But maybe we're keeping them all together in one sort of cohesive grouping, right? So arrays store elements. They maybe store a bit of order, but there's not really an enforcing of the order, right? It's not like just by the actual structure of the array, something at index 0 inherently comes before the thing at index 1. We could use them that way, but that's not like built into the structure of what an array is, right? So we think of these as just sort of categories. Then we did add this next sort of structure up, this thing called a tree. And a tree inherently does kind of have a hierarchical ordering to it. Like if we just wanted to store a bunch of numbers, unless we wanted to sort of like traverse them in, like an ordered way, it would make more sense to put them in an array, right? But like a tree inherently in the actual structure of the data there's some idea that like this is the parent, and that parent might have some relationship to the children. So now we're starting to kind of like bake in relationships between the data. And so far we've seen that in like a binary search tree or an AVL tree, where at least the relationships are ordering, that we've got like an ordered set of things. Like this data comes earlier, this data comes later. And then the same thing with the heap, right? We started to get this idea of maybe like priority or something where, you know, like parents and children have a relationship. And so there is some kind of relationship, but there is inherently limited connections. Like so far we've only done, you know, each node can have at most left and right child. There's really only this sort of like from the top of the tree down to the bottom of this tree type of structure. So we've got this sort of like hierarchical organization, which is taking us, adding in a little bit more relationship than the array. If you can kind of see where I'm headed with this, we're now heading into graphs, where now we're going to do away with all of the limitations on how we structure these things, and we're moving further away from just sort of like the categorical and far more into the idea of trying to represent relationships. Graphs are all about how you represent the relationship between your data. And in fact, we're now going to be adding in different variables. So now we have more than just n to account for. In arrays and trees, I would ask you, what's the runtime in terms of n being the number of items stored within that structure? Now we're going to start talking about nodes, which are sort of the circles here. We're going to actually start to call them vertices, and the connections between these things, the relationships, otherwise known as the edges. And we're going to now need to track our runtime in terms of both the things stored and the relationships between them, the vertices and the edges. Graphs, technically a tree is a type of graph. Same way that like a square is a type of a rectangle but with more specific requirements on it. A graph is sort of like that more generic idea that we have an object, and that object has a connection to another object. But in this case, that connection does mean some type of relationship. We're going to talk about what that means. So here now we've got connection freedom. Each object can connect to as many objects as you want. They can connect back and forth. We're really sort of exploding away from any structure so we can get closer to something that will allow us to represent the complexity of the real world. And that's part of the reason that I'm like obsessed with graphs, is because the real world is messy, right? It's analog. It's hard to map it into a computer. And graphs, this freedom of representation, actually becomes a much easier symbolic way for us to take what's going on out here in the human world and transform it into something that the computer can do something with. And in fact, I'm going to be teaching you a bunch of algorithms that once you can do this sort of mapping from the human world to this, then we can run algorithms over this stuff and learn really important things. The other reason graphs are super important is they're really useful for the reason I just said. You will use them in industry. They do come up in interviews. There is a method to this madness, I promise. So, graphs. Yay, star, we're here. Technically everything is graphs. You've been using graphs all along. Binary search tree, technically a type of graph. Linked list, technically a type of graphs. Heaps, technically a type of graph. Yes, those are all just graphs with much more specific requirements. But you've been using graphs anytime you touch a computer. Some of the ways that our brains might associate with graphs the most quickly is, for example, Google Maps, where we have this idea of sort of destinations and then how to get from one destination to another. So we have these little nodes, those vertices, maybe those are like addresses, and then the edges, the relationships between them are streets. We're going to talk about that analogy more than I care to, because graphs and maps, physical maps, are incredibly good compatriots. Also, whenever you do a search, like let's say you are doing a web crawl through the internet. A web crawler is something that lands on a web page and then just clicks through all the links to get to other web pages. Technically, that's a graph search. Each of those vertices is a web page, and then each of those links, those hyperlinks, are the edges that take you to other places. And so there's a lot of algorithms that help us understand how we navigate the internet. Facebook uses a graph search in its search bar. GitLab repos how they fork from one another, pull in, the includes, the import statements, all those connections, how we come up with the different set of things we need to compile. Those are all graphs. All of this stuff has been built with graphs under the hood. I'm going to do my best to give you as many of these examples as we can as we go through the graph unit. Here is some more applications. So physical maps, airline maps, traffic maps, all of these things where the destination is that little circle and how you get between the destinations. So for example, maybe we have a map of, this is actually a map of, I believe, airline routes. So each airport is perhaps a vertex in this context, and each plane route is an edge. Relationships like social media relationships are another thing that looks great on graphs. So here, this I'm pretty sure is an image I pulled of different Twitter users and their respective followings. So we probably are aware that there's individuals on social media that have a lot more connections heading in to them, kind of thing. So you get these sort of hubs. And maybe you need to figure out how you're connected to somebody by all of those followings. So in these things, you could see each of these dots maybe represent a profile, and each of the lines represent a follower type of relationship. And it lets us sort of map these kind of like heat maps of connections between people. Code bases, same thing, where maybe an individual code file is one of those sort of like nodules of item. And anytime you include an import statement is technically a request to go out somewhere and grab a piece of code. That's like a way of your code saying, I'm connected to something else, I'm using something else. And so actually the way that your computer goes in and determines which files need to get recompiled and transformed into class files when you hit that build, they made a map. They made a node that's your file, and they include edges for each of those sort of connections. Also, other ways to think of maps. Influence. This is another very common usage. Computational biology, obviously a very close kindred spirit, a cousin of computer science, if you will. Computational linguistics, things where we've got this idea of some type of entity and then the influences on that entity. I'm going to be real. I don't know exactly what this picture is. I stole it from a very cool website who I just realized that its link is maybe not on this slide anymore, that specifically just went through and found cool graph applications, but I'm pretty sure this is something that represents the different protein influences within the computer or within the body. Ooh, Freudian. So influences, for example, like maybe, I am a particular vital organ and I have different proteins coming into me. Those kinds of things can be represented in this way. And then that data, once it is digitized, can be fed into computers, and then we can apply machine learning, artificial intelligence types of algorithms on top of it. Also, sort of related topics, web page rankings, we talked about that. So each page is connected to another page by hyperlinks. You can imagine that if you have a bunch of web pages hyperlinking to one in particular web page, i.e. maybe there's a really influential post or paper or something, and a bunch of other pages link to it as an influential thing, that actually drives its SEO, its search engine optimization, up. That is how Google determines some of who gets surfaced in what order when you search for something. So we have to map those connections and figure out who is the most influential hub node within the internet. You can do the same thing on Wikipedia. It's a little easier maybe for us to see it on Wikipedia because Wikipedia is just text and hyperlinks. Yeah. Say it one more time. Is the internet just one big graph? Kind of, yes. And the weird thing about it is it's kind of multiple graphs stacked on top. So there's the theoretical graph of you have a HTML document, and then you have the hyperlinks between the HTML documents. But that HTML document, it might be something you write on your local machine. It could be something that's stored on a server. So that is sort of like this theoretical graph that we want people to be able to navigate. The actual routing system that connects your packets along all of the different wires, that sort of idea that there are hubs and routers that send information, also a graph. Yes. And in fact, the I don't know if anyone's familiar with the ARPANET. That was technically what was invented before the internet. It was invented for university systems in order to share things. It was actually invented during the Cold War intentionally to be decentralized so that nobody could nuke any particular area and we wouldn't be able to connect, built on graph theory. Yes, so all of these things. Graph theory actually does predate computer science for reference. I will fully admit when I say graphs, I mean like computer graphs, but if you are a wonderful mathematician in here, maybe you know even more about it than I do. But a lot of the stuff we're talking about existed before computers, but now computers, by translating it in this way, lets us do all of the really complicated math and to create those models and patterns that computers are really good at sort of pulling out and then running types of algorithms over. So another good example. Oh, there's my thing. There. That's my, I was like, there's our link. You could go look at this and read more about it. There's so many more applications of this. So those are all of my, like, aren't you excited to study graphs with me kinds of things. Let's talk about what a graph is by formal definition. A graph, by definition, is defined by a pair of sets, V and E, so two different collections. Sometimes they'll look like this. V stands for the set of vertices. These are the vertex or node. These are the individual data entries. You'll see I kind of represent them by these circular purpley kind of things. So maybe in this graph that I have on the page, my set of vertices are A, B, C, D, E, F, G, H. The second set is E for edges, and that is the representation of the connection between any two vertices. So in this particular example, you can see that we have a connection, right, between A and B. That's this line right here. We also have a connection between A and C. We also have a connection between A and H. We also have a connection between A and D. And those are all the connections for A. So you can see those are our 1, 2, 3, 4 little entries there. And so then our set of edges is represented by which two vertices can be connected. So this is the formal definition of it. Any questions so far? Yes?
Does an edge only go in one direction?
Great question. Does an edge only go in one direction? It can. Right now, you'll see these edges, if you can tell, they don't have an arrow on either side. Remember in our trees, we always draw them with arrows because in that case, there's always only one direction. Like a parent can only travel down to its children. Children usually don't have a connection up. And so in that case, those edges are singular directed. Because there's no arrows on these are what we would call bi-directional edges. So what this would mean is if we, again, go back to our like Google Maps example, this would be maybe like two-way streets where I could drive from A to D and then I could turn around and I could drive from D to A. And those are both represented by this set. But that will be a specific thing that you will want to ask about every single graph, whether this graph includes bi-directional edges or single directional edges. Let's add some more vocabulary in. So there we go. Undirected, that's what we just looked at, which means there's no arrows on any of those edges. And if there's no arrows, that means every edge is both ways. So there we go. We've got an undirected graph, you know, like Karen is connected to Jim just as much as Jim's connected to Karen. And same thing with Pam. Sorry, Kim and Pam and Karen. So there we go. There's how we might represent those two sets. We could have directed graphs. So there you go. We've added our little sort of arrows, right? So we know that Gunther is putting a lot of directionality towards Rachel, but she has perhaps not noticed and has made a very poor choice and spends all of her time looking at Ross and vice versa. But we should all learn from Rachel's mistakes, shouldn't we? Ross is the worst friend. Okay, so there we've got our graphs. So now that we've got this idea of connections, we also have this idea of degree, where a degree is the number of edges connected to a vertex. Remember, we're maybe in some situations trying to determine if you are a particularly well-connected hub. So maybe you're a web page that gets a lot of people linking to you. You would have a high degree. So in the first one, Karen, Jim, and Pam, I guess technically this is wrong. Jim has 2 connections, so I should change that. We would say degree when they're not directed, but we call them in degree and out degree when they are directed. So poor Gunther has an in degree of 0, but an out degree of 1. And again, I should really change this. Rachel has a degree of 2. Or sorry, that was in degree of 2 and out degree of 1. Yes. What an interesting question. Wait, where is it? Oh, shoot. Hang on. Okay. Yes. So you can have what you just asked. Oh, I guess I took it out. Okay. It was a really good one. Obviously, the example I used for that was Kanye, because Kanye just points at Kanye. You know what I mean? Thanks for laughing, even though I didn't have the thing up here. Yeah. So what you just described is something we will call a self loop. So you can have a self loop, and you might be like, Casey, why would you ever have a self loop? Your edges can store information. That is the other thing about this that we haven't seen. So right now, we can see sort of names in each of these vertices, but the relationships themselves might store information in them. So for example, again, in the Google Maps example, maybe you have a street that stores the incline, like the, so you know how much up or down moving you're going to, or maybe you have an edge that stores the amount of traffic or the distance or things like that. And so if you had a situation where maybe you have a self loop, maybe that self loop represents like a state. State diagrams are also used as graphs. A really common example of that is, why did I just lose the words? Streetlights, that's what I'm saying. So if you think of streetlights, right, like they sort of have different states. Like if it's green, then it's about to go to yellow, and if it's yellow, then it's about to go to red, but maybe it has something that interrupts it and would have it to stay longer on that. So for example, like let's say it has a sensor that can tell somebody sitting on the space in the street. You might have a self loop that adds an extra 30 seconds onto the like red light so that somebody doesn't come crushing through and hit somebody in the intersection. So self loops are definitely also a thing. Here's some more terminology for you. We would say 2 vertices are connected if there is a path between them. A path is a sequence of vertices connected by edges. So in our little examples here, we would say F and G are connected because I can go from F to E to G, so I can get there. We would say G and J are disconnected. There is no edges that connect such that I can get eventually from G to J. And what's weird is this selection of 4 here, that is a valid graph. So you don't have to be connected to be part of a graph. You could have one little sort of person hanging out all by themselves here. But that's, I know. When I first made these slides, this was also in the thick of Game of Thrones, so my one little sad out person was always Jon Snow, because why don't they let him be a real boy? Sad. And so this idea that you might have to store these vertices, though you might not always have a way to get to them. For example, like when you start a social media profile, maybe you don't have any followers, right? Until you start going out and following people and they start following you. So this is also a way for us to start to store data that doesn't have to always be connected. And again, that might tell us just as much about the relationships as the others. So we would say things are connected if there's just any way to get from one place to the other. So for example, down here, O and N are connected because I could go pathwise O, P, I, M, N, or I could go O, P, M, N. Both of those are paths that would take me from O to N. But directionality does matter. Whoopsies. So for example, here, I cannot get from O to N. O and N are not connected because I cannot go back from O to anywhere else because of this little arrow here. But I could say go from I to O because of the directionality there. A simple path is a path without repeated vertices. A cycle is a path whose first and last vertex are the same. So for example, maybe I wanted to like figure out, can I go from N all the way back around to N again without repeating any things? Is there a cycle in my graph? And obviously, like in the tree examples, we might refer to trees now as directed acyclic graphs, because they have directionality. You just go from parent to child, and there's no cycles in a graph. I feel like maybe I brought that up once very previously. But trees technically a type of graph, but they would be a directed acyclic graph. Directed, cyclic. undirected acyclic. You can read these things, as you can see here. Like I said previously, edges also store information. Now, they might actually be objects with fields, but you'll find as we get into the actual implementation of these things that we may or may not actually create objects with fields. We might instead just have a collection of objects with sort of references between them. That will make a lot more sense as we get into the disjoint set section. And for Project 4, your final project, for context, Project 3 is a 1-week project. Project 4 is a 3-week project. I know. We designed it originally to be 2 weeks. I'm just being generous, okay? But it will be a 3-week project because you're going to be implementing a graph, you're going to be implementing a data structure, and you're going to be implementing a couple algorithms on top of it. And then part of the reason I made it bigger is because I know everybody wants a big project to tell the people on their resumes, all that good stuff. So that's what we're doing with Project 4, okay? So you'll find that edges have information in them as well. Often they have at the very least some type of label. So you can see here we've got, vertex and edge labels. A lot of times we think of them, you'll see them most often this way, where the edges have some type of number associated with them, and the number is what we would call the edge weight. So maybe that edge weight is the minutes it takes to drive. Maybe that edge weight is the, if we are, say, doing social media influence, maybe each time you draw an edge, it represents how many followers that person who followed you have. Maybe it's more valuable if, a famous person with millions of followers follows you as opposed to, unfortunately, Casey Champion, who only has so many, that kind of thing, right? So these numbers associated with the edges, a lot of times we call them edge weights. And those edge weights are often what we are using in these algorithms, because often the algorithms are telling us things about how do we get from one vertex to the other in, say, the minimum amount of weights, the minimum amount of steps, how do we even maximize those things? That's often the questions we're asking ourselves. More examples, I'll let you read them. Okay, so here's one thing that we definitely need to talk about. So now we are entering into slightly more complicated analysis because we have added another variable. Previously, we only cared about n, but now we must care about two things. We must care about both v and e. So when I'm asking for the runtime of graphs, you must report the runtime of graphs in terms of v and e. There is no more n in the context of graphs. Will I mess up and say n and probably mean vertices at some point? Yeah, I will, because you will too. We're all in it together, y'all. But remember, we've got two variables here, v and e, and so we'll be saying big O of, say, v plus e is what we would call graph linear, where it's one linear run through all the vertices, one linear run through all the edges. Okay, how do we actually build these things? So like I said, you could make a bunch of nodes, and the nodes could have pointers in them. It will be a nightmare. Very similar to the nightmare of trying to implement a heap with those things. And so we're going to end up in a very similar situation to the heaps. Again, there's a reason we did that before we did these, where there's almost always going to be that kind of top, theoretical graph. But when we're actually writing the code, it might not actually be those nodes with the connection. So here's one way to represent it, very similar to how we represent a heap with an array. This isn't a graph with an array, but it is actually, because it is multidimensional, it has to be a two-dimensional array. So we would call this something an adjacency matrix. So the way that this works here is we have a two-dimensional array, which if you're not familiar, because I know UW is super weird and we don't do two-dimensional arrays in 143, this is an array of arrays. In this class, we are only going to talk about square matrices, meaning where every column has the same number of rows, for example. So these aren't jagged matrices. But in this context, you can see here, I've got that graph up at the top that has the vertices 0, 1, 2, 3, 4, 5, and 6. You can see then that I have 0 through 6 rows and 0 through 6 columns. And to represent that there exists a relationship between two of those vertices, I then go into my adjacency matrix and I flip that particular cell to indicate true. Sometimes people will do these as like Booleans. You might be like, Casey, if it's just true and false, let's do Booleans. But computer scientists, and you'll generally find other languages, are obsessed with using numbers to represent true and false, where 1 typically represents true, 0 typically represents false. So if you can see here, let me see if I can do it with my little mouse. If I come in here, you can see that there's a red 1 right here, which is in the column 1 and the row 0. And that represents this edge right here, meaning I can get from 1 to 0. And because it doesn't have an arrow on it, it's bidirectional. So I can see if I come down here in column 0 in row 1, there's another 1 there because I can technically get back and forth between these two things. So this edge is represented by 2 number 1s inside of this adjacency matrix. You can so on and so forth. Yes. Yes, exactly. So right now, 1 and 3, because there is no arrow on either side of this drawing. If I had put an arrow here, that wouldn't be the case. But because there's no arrow, it's bi-directional. So 1 can get from 3 and 3 can get from 1 to 1. So if I come down here, here's the 1 to 3. Here's 3 to 1. I should put a 1 there. Sorry, this got a little messed up. Yes. Like, how do we traverse through this? A great question. We are going to do something called BFS or DFS, which stands for breadth first search or depth first search, which is some recursive algorithms. And I am going to talk about that. And essentially what you do is you sort of, I think of it as like you kind of like jump in and land on one of the vertices, and then I investigate all of my connections, and I pick one of those connections, and then I can see if I can get there, and then I just kind of keep looping. I promise I have a bunch of hopefully some animations that are not broken that will talk about that. So in this particular case, let's say I was asking the question, is 4 connected to 3? What I would do is I would say, oh, well, let's come down 4, and we'd see, does 4 have any connections? And I'd see, oh, boom, here's a connection with 5. So now I'd come down 5, and I'd say, hey, 5, do you have any connections? Boom, there's a connection with 3. By sort of looking through the columns of this adjacency matrix, I sort of started at 4, asked myself if there's any way to get to 3, took its 1 connection, asked myself if there's any way to get to 3. Oh, boom. Thankfully, 5 was directly connected to 3, so I only had to take 2 edges. But I could have continued that. For example, if I was trying to determine if 4 could get to 6, I'd come in, I'd be like, oh, there's 1, I'd get to 5. Oh, there's 1, I'd get to 3. Oh, there's 2, maybe I'd go to 1. And then I'd realize I kept looping, and I never found a way to 6, and that's how I would determine that 4 and 6 are not connected. So I'm actually sort of like directly following through the paths, just like I would in a tree, right? Like in a tree, you kind of got to start at the top and recurse your way down, similar-ish. Yes?
Is there a convention for like which direction an edge points? Because they both point both ways, so it's hard to see which one.
In the adjacency matrix, I think the convention is row first ordering technically, but you'll find that sometimes it's commingled. Yeah.
In the situation that you just described, you kind of go down each row and check the connections. In this case where it's both ways, how would you avoid getting stuck in the infinite?
And you'll find when we get to that, we are going to need some data structures in order to make this traversal. So previously, we just sort of relied on like, hey, we're like passing in objects as parameters, we're checking that object and we're checking its connections. Now instead, we've probably got like a collection of vertices, a collection of edges, and then we're going to create a separate collection that's like things I've already visited. And before I go make another step, I check, hey, have I already included that in my algorithm, essentially? Yeah.
So the double bar notation,
Mm.
B and P, I'm assuming that's magnitude.
Yes.
I'm kind of wondering why you need magnitude, considering, I don't know, it doesn't seem like you're going to have negative vertices.
You know, that's a really good question. The question's about this sort of notation with the double pipes around the V and the E, and you're right, it does represent magnitude. And you can have negative weights.
Okay.
So, for example, like, I'm trying to think of a good real world example, but like, you know, like let's say that you have a graph representing costs of things, and maybe like positive weights are you like spending money and moving from one state to the other. Maybe negative weight is you earning money. So that's why sometimes that stuff can come up. Just to sort of click through these things. So now in this adjacency matrix implementation, which is only one of two different ways to implement graphs that I'm going to talk about, the runtime it takes to add an edge is constant. Because in order to add an edge, all I got to do is go into my two-dimensional array and change one of these zeros, probably two of these zeros, to a 1. And that's constant, right? Constant time. If I want to remove an edge, again, constant time. I just come in here and take a couple of these 1s and I transform them to zeros. If I want to check that an edge exists, again, constant time. I'm just checking elements of this two-dimensional array. If I want to get all of the out neighbors, then that might be a situation where I have to sort of like run through everybody and be like, hey, 0, do you point to 3, 1, do you point to 3, 2, do you point to 3, so on and so forth. So I'd have to do that versus in neighbors, maybe I have to do something similar. So there's some of the kind of runtime of these things. The space complexity, this needs to be, okay, I figured this was broken, hang on. Okay, there. I just want this to look like this. Sorry, these slides in particular were a problem this morning when we were trying to fix them. I'll have these all nice and cleaned up and post on the website a little later. But this adjacency matrix implementation, as you can tell, it's really inexpensive to add edges, remove edges, determine edges. If I had to add or remove a vertex, that's when it becomes a lot more expensive. Because the vertices are currently reliant on how many like elements of the arrays there are. So if I were to say create a new vertex, I'd have to recreate this whole adjacency matrix. So adjacency matrices are really good when you have graphs that are not going to grow or change in terms of vertex, but might grow or change in terms of edges. They're also what we would call really good for dense graphs where there's a lot more edges than there are vertices. Now, I show you this one first because we're going to move on to this one, and then I'm probably not going to talk about adjacency matrices that much because you'll find they're actually the less popular implementation because of those reasons that I just listed. You'll find most graphs are kind of thought of as vertex first. A lot of times we think of profiles as like the main unit and then the following is less important, right? Also, usually the vertices change quite a bit. And this idea of a dense graph is actually quite rare. Usually there's more vertices than edges kind of thing. So you'll find that in implementation, adjacency list is the type that comes up a lot more often. And the type that you will implement in P4, yeah? So what is this adjacency list situation? So an adjacency list is where we have some type of overall collection, and that represents the number of vertices. So here we've got an array, and that array will say each array can be a bucket. Each index of the array can be a bucket, and that maybe is then some type of collection. So here we've got a bunch of linked lists, and so what this means here is this bucket for A says that there exists a connection from A to B and a connection from A to C. And if we look up here now, we've got a directed graph because there's arrows on it, and we can see those are the two out connections from A to C and A to B. So those are the two things in the collection stored in the bucket for A. If I go to B, we can see B has no outward connections, so B has no linked list. If I look at C, C points to B and C points to D, so those are the two things in its collection, and so on and so forth. So you'll find that often this is the thing that we use a lot more often. We end up with a space complexity then of n plus m, where vertices is n and e is m. And this can be a little bit more flexible for us depending on what we pick. And the thing that will really mess with your brain is technically we can pick any collection here on the left, right? It could be an array. It could be a list. And we could pick any collection here on the right. Those could also be lists. They could be array lists. They could be hash tables, right? Anything that sort of collects together vertices. So a graph, then in implementation, ends up being a collection of collections. Technically, a two-dimensional array is an array of arrays, right? So this is just a collection of collections, slightly just more generic form of it. Also part of the reason this comes up in interviews all the time, because collection of collections is the type of question that people love to ask in interviews. So yeah, here is an implementation, for example, with hash tables as a adjacency list as well. And so in that case, that might be a little bit faster lookup time, which is kind of nice, but a little less flexible, right? So it's sort of up to us how we want to design these graphs. With the linked list, it was much easier to, like grow the number of connections, right? We don't have to do that sort of rehash and resize at any point, but we might have to loop over a linked list to see all of my connected things as opposed to use a hash table to do instant lookups. So again, this might be the way you write it in code here on the bottom, but it's representing that visual up at the top. So just like we're probably going to do with P3, never lose track of that image up at the top. Often I will be drawing these things as we go to make sure that my code's mapping to those. Yes. Okay, here's some stuff about trade-offs. So yeah, adjacency matrices take more space. They're usually good for dense graphs. I mentioned that. Trade-offs between linked lists and hash tables. We sort of mentioned that as well. So for this class, specifically, we're going to almost always be using that adjacency list implementation, and specifically, we're going to probably assume that you have some type of array that is an array of hash tables. So we are going to optimize for that lookup time for determining whether or not there's a connection between two indices. Okay, any questions on those items? I think, okay. Perfect. Then you know what? We'll leave it there for today, and we're going to pick back up, and I'm going to talk through those first algorithms that we asked about earlier, that breadth first search, depth first search. We'll do that on Wednesday. Keep your eyes peeled for the simulated midterm staff solutions getting posted later tonight at midnight. Happy to answer any questions you have on Wednesday. Thanks so much, everybody.